All right, part number 2. You just got done watching part number 1. Here's part number 2. We're on number 4 in the solution traits notes. It says solubility, and then letter A says 100 grams of water. So what this stuff is, this is not anything that you're ever going to have to memorize. I'm just giving you some data. If you have 100 grams of water, you got a glass of water, right? And we're going to dissolve salt in it to make some salt water out of it. That salt will hold at 25 degrees Celsius, which 25 degrees Celsius is considered to be room temperature. It'd be like 70 degrees Fahrenheit. It will hold 36.2 grams of salt. That's the maximum you can put in there. If you try and put 37 grams, it won't hold it. Right? It'll hold all but 0.8 grams of it. 0.8 grams will still be sitting down at the bottom because there's not enough spaces to put that salt in there. Now, we take that cup of water and I throw it in the microwave and warm it up and get it all the way up to 100 degrees Celsius. It means the water's boiling. It's 212 degrees Fahrenheit. Now I can put more salt in it. I can, according to the notes there, we can raise it up. We can put 39.2. I can actually put 3 more grams of salt inside that cup. Why? Because I just opened up these little holes right there, made them bigger. Because they're bigger, I can put more salt into it. Okay. Now, if I put the maximum amount, if I put all of that in there, whether it's 25 degrees Celsius and it's 36.2 grams, or it's 100 degrees Celsius and it's 39.2, depending upon the temperature of that water, it's called saturated if it has the maximum amount of solute in it. If I put the maximum amount of salt in there, then that's saturated. Anything less than the maximum amount is unsaturated. It's not saturated. That's what means. It's not saturated. Anything less than the maximum amount. All right, so if we put the maximum amount saturated, less than that, unsaturated. But you know what? We can trick water molecules to actually hold more than they're supposed to. If we do that, that's called a supersaturated solution. And it happens to be letter V, which is Roman numeral 5. And what we have to do in order to do that is we are going to heat that solution, make those little pockets get bigger. We're going to stick that salt, or we're going to stick some sugar inside of it, either one, right? And then what we do is then we set that liquid down. We just let it sit and let it cool really, really slowly. Right? Don't put it in the refrigerator. Don't put it in the freezer. Just let it cool down to room temperature real slow. And if we can do that, what it'll do is it'll actually stay far apart, and that solid will stay suspended in between. And what it does, it actually makes that liquid hold more than it's supposed to. Now, once it does that, then now that's just sitting there going, man, I want to get rid of this stuff, but it can't get rid of it unless I put something inside of it. I put a little bit of sugar. I put a little bit of salt in it, and let's go with the idea of sugar, simply because of what I'm going to talk about in a minute here. As we put one little stick with some sugar on it in there, then all of a sudden those little crystals will go and they grab a hold of it, and it forms a whole bunch of crystals on that stick. What are those crystals? They're sugar, and that's how we make rock candy, right? And rock candy is really just sugar that came from a supersaturated solution. All right, so what you do find in the case of making a supersaturated solution is I can't have any of this down the bottom, right? If I'm going to make it supersaturated, everything that's in there has got to go up into these pockets. If I have any leftover sugar in the bottom of the cup, then that's going to cause these particles up there, when it cools, to go, and they're going to grab a hold of that. Oh, there goes my light. Hold on. All right. Sorry, I know that light always goes off. What it is, I got to have movement in my room. And when I'm here by myself, there's not enough movement to keep the light on longer than 20 minutes. So then I got to go walk over, activate it again, make some movement in a specific spot in my room, and then the light pops back on. That's why it does that all the time, just in case you're wondering. All right, so in the case of this rock candy, the whole idea is if we have anything down here, then these particles are going to fall back down to the bottom, right? So the only way you can make a supersaturated solution is if you put stuff in here and you get it to dissolve when it's hot, and then you let it cool really slowly. Then you can make a supersaturated solution. And you can actually make your own rock candy at home by making a supersaturated solution. So, all right, moving on, letter B, increase the pressure, increase the solubility. And this is a liquid and a gas. What we do is that to increase solubility of carbon dioxide, Right? In other words, put more carbon dioxide into a bottle of pop. What I actually have to do is I got to raise the pressure above the can. So if I'm trying to put carbon dioxide in here, what I'm going to do is I'm going to put carbon dioxide into this can, and I'm going to force it down in there really, really hard. And I'm going to put a lot of pressure into it. As I put pressure into it, I can force that carbon dioxide into there. Right? If I release the pressure and I go like that, then you always hear that thing. That's the carbon dioxide getting released because it's not being held down inside there. If I left this can open like that on my desk all day, do I still have carbonated pop by the end of the day? Probably not. It's going to be all flat because there wasn't the closed at the top, so the carbon dioxide was able to escape. It wasn't being held in there, right? So if I increase the pressure, I can actually increase solubility. Another way in which I like to describe this is kind of like putting a nail into a board. If I had a board sitting here and I put a nail on it and I took a little bitty hammer and I went a ding, 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 and I just barely hit it, is that nail going to go into that board very well? No, probably not. I'm probably not even going to get it into the board hitting it like that. But if I took a big old sledgehammer, a big hammer, and I took that nail and had it there and I went, oh, wham! And I hit it really, really hard, is the nail going to go into the board? Oh my gosh, it's probably going to go all the way through the board, probably into my hand. That's not going to be a good thing. So because I put lots of pressure on the nail, then the nail goes into the board. Same idea with this carbon dioxide that's in pop. Right? Put a little bit of pressure on it, I get a little bit in there. Not very much. Right? If I put a whole bunch of pressure on it, then I get a whole bunch of carbon dioxide to go into it. Right? And that's actually what chemical engineers will do as part of their job is they identify how much carbon dioxide goes into this. Right? And they actually measure it. And as the Coke is being manufactured in the factory going across, they'll take one piece of Coke off of it, one can, and they'll test it and see if it's got enough carbon dioxide. And they take it over and they do a test on it. If it's not got enough carbon dioxide, then they go back to the front of the line and they tell the person that's running it, raise the carbon dioxide level, raise that pressure and make it so it puts more in there. And then they'll run a few more and then they'll take one off, check it. And if the carbon dioxide level is higher, then they go, okay, now we're good. Or if it's too high, then they go, okay, turn it down a little bit. We're wasting too much carbon dioxide. These cans are going to blow up. So they turn it down a little bit and they try and get that right in the right spot. And that's what the chemical engineer does that works at Coca-Cola, is they're trying to make sure that they have enough carbon dioxide inside these. So when we buy it and we open it, it goes psh, and we're happy with it when we taste it. What we don't want to do, and neither does the chemical engineer, he doesn't want you to open a can of Coke and go, I think it didn't go psh. That's no good. This Coke's going to be flat. It's going to taste nasty. I don't want that Coke. I want Coke that's got a psh to it. That makes it taste better. So now all of a sudden I'm going to take this thing back, and then Coca-Cola lost a bunch of money because they sent out something that wasn't carbonated. And now they got to take it all back, and that's going to cost them a bunch of money. So they don't want to do that. Right? Now at the end on this, there is actually a little calculation that you can do. It's called Henry's Law. What we can do is we can actually calculate that solubility based on pressure. And I'm going to get rid of this, because we're done talking about that now. And what we can do is we can go solubility 1 over pressure 1 equals solubility 2 over pressure 2. So what we do is we actually have two systems on this. Okay? And Henry's Law says, according to your notes you should have written down, is that at a given temperature, the solubility of a gas in a liquid, S, that's this, solubility, is directly proportional to the pressure, P, right, of the gas above the liquid. And that's where you get this real quick equation, right? So then I gave you one in your notes that said a given solubility of gas is 3.6 grams per liter. So I'm going to give you that. It's got a solubility of 3.6 grams for every liter of the liquid. And that's going to be at a thing called 1 ATM. Well, what in the world is an ATM? Right now, I know you don't know that yet, but what it is, it's a unit of pressure. Right? And we're going to get to that later. I would love to give all of this stuff to you immediately, but what ends up happening is it like gives you an overload and gives you too much. So right now, I just want you to know that ATM is a unit of pressure. So that means we're going to put that in the spot where it says pressure. Now it says find the pressure, its solubility goes up to 9.5. So if I want this thing to go all the way up to 9.5, what pressure do I need? Now, I made a little chart there, and what I have is, in this chart, let's see, do it over here, we have S, oops, sorry, try that again. We got S and P, right? And then I have, in the chart, I have system 1 and system 2. So now I can go back and I look at the things they gave me, and they said, well, we got 3.6 grams per liter. That was the first solubility, and that's at 1 ATM. And then we have, well, it says, what if we raise that solubility to 9.5 grams per liter? And what X is going to be the new pressure? So now what I have in this chart is I actually have everything I need for this thing. Well, this spot right here, that's S1. This spot right here, that's P1, which goes with this. And then I have S2, and I have P2. So now I'm going to just substitute it into this, and I'm going to go, well, S1 happens to be, let me change colors. S1 is going to be 3.6 grams per liter. P1 happens to be 1 ATM. Then I go to S2 is 9.5 grams per liter. And P2 is my X. Now from there, all I got to do is cross multiply and solve. I do like to point out what cross multiplication is. That's where you take the top here and multiply it by the bottom. Take the top one here and multiply it by the bottom. So I get 3.6 times X equals 9.5 times 1. Now I just got to solve for X and get X all by itself. I know this is math, but welcome to chemistry. Chemistry is a lot of math. Try and keep it as easy as we can, but there is some math we got to do. So we're going to divide both sides by 3.6. That lets me get rid of these, and now I have X equals something. So now you can use the calculator that's on your computer and take 9.5 times 1, which is really 9.5, divide that by 3.6, and you are going to get an answer of 2.6 ATMs. All right, ATMs, that was our pressure. That's what we were trying to find out. Now, does that mean the pressure went up? Well, the pressure was 1 ATM. It changed to 2.6. Is that bigger? Yeah. So the pressure did go up. It's greater now. We have a 2.6 ATM pressure. So I got to raise that pressure if I want this much of that gas to be inside my Coca-Cola can. All right. All right, well, that concludes the notes. Actually, I believe concludes the notes for this chapter. So we're near the end of this chapter. So we'll see you next time.